In this video, we're going to be doing an AP Physics 1 FRQ on the effects of changing gravity on projectile motion. So we have a ball is launched from ground level with a speed of v initial at an angle theta above the horizontal on Earth, where our gravitational acceleration is g. That same ball, mass, is going to be launched with the same initial speed at an angle on a different planet, where the gravitational acceleration is going to be 2g. So our angle is going to stay constant. Our mass that is being launched is going to stay constant, and we are going to have the same v initial that is going to be the speed that our object is launched on both of these planets. The only thing that is going to be different is that we are changing our gravitational acceleration, which is on Earth going to be just g, and then on our other planet is going to be 2g. So first we're asked to derive the expressions for time of flight on both planets and determine how they compare. Well, the first thing we can do before we do that is, because we have velocity, we have to break this up into components. When you have your velocity vector, you're going to have pointing in a diagonal at a point, but that is going to have a vx, which is your horizontal component of velocity, which is equal to the velocity times cosine of the angle. And your vertical component is going to be equal to v sine of the angle. Now, in the horizontal direction, let's talk about our motion. We are going to have acceleration that is equal to 0 in the horizontal direction, which is why our vx in the horizontal direction is going to equal to your v initial x, so it's going to stay constant. Now, what about in the vertical direction? In our vertical motion, we are going to have our ay is equal to negative g. So if we use kinematics for our a time of flight question, we are going to have that we want to get that total time until the projectile returns to same height, which means that if we set this as y is equal to 0, we want the time again when y is equal to 0. So we're measuring that time duration. Therefore, our kinematics equation is going to be that vertical equation where we have y is equal to v initial y t minus 1/2 gt squared. So then you can plug that in, and you're going to have 0 is equal to v initial y t minus 1/2 gt squared. Again, our acceleration is equal to g, so you can substitute that in for your g right there. Now you could factor this as well. You have 0 is equal to t times v initial y minus 1/2 gt squared, or just gt, because we can take out one of those t's and then one t is left on the inside. Then we are going to have two solutions by using the zero product property, where we get that either t is equal to 0, which makes sense. So this is going to be our first occurrence of when this happens, because we know that this is going to happen twice in the duration that we're measuring. We're measuring when it starts at the ground until it returns back to the ground, so that is obviously going to be the first time. So we're going to want that second time. So then we set our v initial y minus 1/2 gt equal to 0, and if we set that equal to 0, we get that we can add 1/2 gt to both sides. If you do that, you get v initial y is equal to 1/2 gt, and after this, we can multiply both sides by 2, and if we do that, that cancels out. So here, after this, we just want to isolate our t, so we can divide both sides by g, and doing that, that g cancels out. Now our t is equal to 2 times our v initial in the y direction times sine theta, because v initial y is also equal to our v initial sine theta without that y component. So this is v initial sine theta divided by our gravitational constant. So this is going to be when we are on Earth. Now this is going to be called, let's just call this planet 2. So that is Earth. Now for planet 2, the only thing that is different about planet 2 versus our planet is that we are going to have twice that gravitational constant. So everything's going to stay the same in the equation, except you're going to have a 2g here instead. So then if we take the ratio of these two, then we are going to get that t prime, aka planet 2, is equal to t divided by 2. So our original Earth time divided by 2, because we have that 2 in the denominator of planet 2. Now, for our next question, we want to find what the maximum height is going to be on both of our planets, and we're going to determine how they are going to compare to one another. Now, in order to do this, we know that when you are at max height, this means that you have your vertical velocity is equal to 0. So what that means is that you're going to have Vy squared is equal to V initial y squared plus 2 times your acceleration in the y direction times the change in your vertical height, y. So then if you plug in your values, we have Vy is equal to 0, right? So let's just highlight this in another color. We have Vy is equal to 0. So then we can have here a Vy. We can plug that in. So we're going to have 0 squared is just going to be 0. And then we have our V initial y squared minus 2. Our acceleration in the y direction, again, was equal to g here. So we're going to have negative g, but we can move that negative out there. And we have our delta y. So our delta y we'll just call the height. And we're then going to make this our height. So then back to our equation, we are just going to solve for this now. Now we can add this 2gh to both sides. And when you add 2gh to both sides, this cancels out. You're going to have 2gh is equal to V initial y squared. Now, what you want is to just isolate your height because we're getting that max height. So height is going to be equal to divide this side by 2g and this side by 2g. So that is going to be h is equal to V initial y squared divided by 2 times the gravitational constant. And we know that V initial y is equal to V initial in general squared sine squared theta. Because all we did here is, for this step, we had V initial sine theta, and then we had that this was squared. So then we just multiplied them by each other. For this step, you had V initial sine theta times V initial sine theta. So then you multiplied, and then we got this. So that was just all over 2g. Now, this is going to be when you are on Earth, though. However, when you are on your planet 2, we are going to have h prime, not our normal h, because we have twice the gravity. So that means you have V initial squared sine squared theta, which is going to be over 2 times g, but this time we have twice g. So now you can multiply that 2 and write the simplified form, where you have a V initial sine squared theta is going to be divided by 4g. Therefore, if you take the ratio of those two, we can see we have h prime is going to be equal to h, the exact same value that we have for h. Everything is the same, except you would just be dividing by 2 for your entire result of h that you would get from planet Earth compared to planet 2. And this makes sense because we know that gravity reduces how upward motion can go. So our answer makes sense logically. Now for our next question, we are asked to determine the expressions for the range on both planets and determine how they compare to one another. So for this question, for range, our range is equal to our horizontal distance that we travel when we are on that projectile motion path. So over here, our range is going to be this delta x. That is what our range is. We're trying to find that horizontal distance that we traveled. Now what that means is we can simplify our kinematic equation to our x is equal to vxt. So then if we have our horizontal velocity, which we know that Vx is equal to V initial cosine of theta. So then in this equation, we have this, which we substitute in for this value. We have V initial cosine of theta. And then we have our time expression. Our time expression is equal to 2V initial sine theta, all divided by G. So we would take this time expression, and we would take that, plug that into our equation here. And that is our x. So then we can see that we have a twice times sine, and then we have 1 cosine theta. So we know that if you have 2 sine theta, right, and you have 1 cosine theta, does this look familiar? Well, it's our double angle identity. And this is equal to sine 2 times the angle theta. So that's sine, and then that's twice the angle that you input into sine. So then we can rewrite this as x is equal to 2v initial squared sine theta cosine theta over g. And then we plug in with that form. So now our final range formula, x is going to be our horizontal distance, right? So these all are going to mean the same thing. This is going to be equal to v initial squared sine times 2 the angle theta divided by g. So this is going to be on planet Earth, though. But on planet 2, our only differentiating thing was that we had twice our gravity. So you have this exact same formula, r is equal to v initial squared sine times 2 of theta, except you're going to divide by 2g instead of g. Now, what can we see is the difference? This is r prime, by the way. So r prime is going to be equal to r divided by 2. The reason being that 2 is in the denominator. And you can just examine in the equations that everything is the exact same. See, everything in this equation is the exact same as our Earth planet, except the only different thing is that we have division by 2 in the denominator, which is why we say that when we take r prime and we wanted to find that in terms of r, we would just divide r by 2. And this makes sense because if you have less time in the air, that's going to mean you have less horizontal distance. Now, for part D, we're going to be asked to determine the horizontal and vertical components of velocity at the launch, and we're asked to compare between the two planets. And then for part E, we're asked how the shape of the trajectory changes when our gravity increases. Now, in order to do D, to find our initial velocity components, again, as a reminder, v initial in the x direction is going to be v initial cosine theta, and v initial in the y direction is going to be v initial sine theta. Now, what if these components depend on gravity? Is it going to be different when you are on Earth versus planet 2? No, there's going to be no difference because there is no g in either of these equations. So that means that our components are going to be the same on both planets. And that's because our initial velocity is set by launch conditions only. There's no gravity inside of either of those equations. Now, for our trajectory shape, we can backtrack for our horizontal motion. What influences our horizontal motion, What will influence the shape? Well, the shape is purely dependent on x is equal to v initial x t with no gravity present. And vertical motion is only going to be dependent on y is equal to v initial y t minus 1/2 gt squared. And that g makes sense because, again, gravity is always acting in that vertical direction downwards. So why would gravity be affecting the horizontal motion when we're only looking at this horizontal direction? In vertical motion, we're only looking at up and down. And these two comparisons of horizontal motion and vertical motion are separate from one another. You don't compare them together. They're completely separate, and you don't want to think that either one of these affect each other, because when we're considering them, they happen in different planes. Like, we don't consider them together. And only when we're taking the magnitude, we're going to combine both of them with the Pythagorean theorem. Now we're going to think about the effect on g. So we see this 1/2 gt squared. If you increase g, this is going to have a larger effect. So that means that the object would fall faster. However, in horizontal motion, if you have a increase of g, you're going to have the same horizontal motion. Now, the only thing that's going to change is that you're going to have a faster vertical drop. So our answer is going to be that our trajectory becomes steeper and more compressed. And what that means is that in the same range, right, you would have something like this. But then in that same range, it would become something like this. So one is really steep, one is less steep.